Okay, in this video, we're talking on hybridization of carbon. Okay, hybridization is the mixing of two or more orbitals to form a higher orbital of different energy and shape, which is better disposed for chemical bonding. The original orbitals are called the pure orbitals. The original orbitals before they are hybridized, they are called the pure orbitals, while the new orbital is called the hybrid orbital. The new orbital formed when the two pure orbitals are actually, or two or more pure orbitals are actually mixed, is called the hybrid orbital. Now, there's a reason for hybridization because why will a compound just hybridize, just combine like two orbitals? Why should they just combine and form a new orbital when they can actually bond singly? The reason for hybridization in carbon is because the hybrid pair is more stable than the pure pair. So, like the hybrid pair, we all know that in chemistry, like everything is mostly about stability. Once like all the compounds, like if I put it, they're always trying to be stable. The most stable form is what they always attain, and that's the major reason for hybridization. Now there are three types of hybridization. There's the SP hybridization, the SP2 hybridization, and the SP3 hybridization. We'll be talking on all of this as we go further. Now the SP hybridization. This occurs between the s orbital and the px orbital only. Now we've talked about the s orbital and the px orbital in our previous video, so let's continue with that. We know the shape of the s orbital is spherical and the shape of the px orbital is dumbbell in the x direction. It is found when carbon is touching a triple bond. They include alkynes, cyanides, and so on. The compounds are linear in shapes. The bond angle is 180 degrees. The percentage characteristic of the orbital. Now the percentage characteristic of the s orbital in this is 50 and the percentage characteristic of the p orbital is also 50. Now let me describe the percentage characteristics. Now we all know that they are all like, if I put it, 100% is like total percentage characteristic. Let me put it this way. There are two orbitals. Share 100 in two. We'll have 50% to one and 50 to the other. Since there are only two orbitals, S will take this, PX will take this. So it's actually self-explanatory. Now I'm going to draw on how all these orbitals are formed, on how the S orbital combined with the PX. I'm going to like represent it diagrammatically. Now the s orbital in our previous video, I've told you that it's spherical, and the px orbital, I told you, is a dumbbell shape in the x direction. This is my s orbital, this is my px orbital. So when these two orbitals combine, they form the sp. We don't call it spx, we call it the sp orbital, because like the sp hybrid orbital, because we have to call it like with the general name. We don't have to like break it down to px, py, and pz. So now this combines to form a new orbital. Look at the way I'm drawing this new orbital. Now if you look at it now, it looks like it's only the p orbital, but when you look in between both dumbbell, like in between both loops, you will find out that I added like another baby loop, if I call it that, and that's the s orbital. That's what it is. This is the s orbital. They are located in between them. They don't form to like cover the top. If you do that, you'll be wrong actually there. So now that's the s orbital. I told you it's found in cyanides, it's found in alkynes. So like in alkynes, we all know it to be this triple bond. We'll discuss this further videos. In cyanides, we all know it's going to be this. Nitrogen has three. Nitrogen has three. Nitrogen will have to take 3 electrons, if I put it that way. Okay, now we are done with the sp hybridization. Now let's go to the SP2 hybridization. I'm sorry, I'm coming. SP2 hybridization. This occurs between the s orbital and the px and px and py orbital, if I put it that way. These two orbitals, they actually combine with the s orbitals to form the SP2 hybridization. This hybridization is found in alkenes, carbonyl compounds, carboxylic compounds, and carboxylic derivatives. Carboxylic derivatives include esters, they include amides, alkanoil halides, alkanoil anhydrides. I mean acyl anhydrides and all those type of compounds. This it's formed when carbon is touching like a double bond. If I put it like carbon is touching a double bond, it is trigonal planar in shape. It has a bond angle of 120 degrees. The percentage characteristic of the orbital now is given, like the s orbital alone is 33.33 degrees, and the 2p orbital, they sum up, sorry, there's meant to be a gap between that, they sum up to 66.7 degrees. Now, like I did in the SP hybridization, let me show you how to calculate it. Like, there are three orbitals actually. When we sum the s and the 2p orbitals, we have, let me call it three orbitals. That the three orbitals now. Sorry for that. So when we divide 100 into three places, we have 33.3. So now let's divide, like this 33.33 is going in three places. So this can be given to s. Then 33.33 times 2 can be given to the 2p, and that's 66.7. Okay. Now that's it. Like I did for the sp orbital, I'm going to be doing the same for the p orbital. Now I'm going to be drawing the shape of the SP2 hybridization. First the s orbital, then next this is my py orbital plus, then this is my pz orbital plus, okay, this is my px px orbital. So watch this. When they combine, I need space, so I'm going to like be erasing this. When they combine, they form this. It's not going to be like what you think. This is it. This is what they form. If you look in between here, you actually see the s orbital. Now this shape is the trigonal planar. The bond angle, like I said before, is 120 degrees. Why is it the shape? This is what they form when they mix. I'm not the one who actually like formed this. This is actually what they form when the three orbitals actually mix, or should I say hybridize. Now let's go further. Now we're going to be talking about SP3 hybridization. The SP3 hybridization, this occurs between an s orbital and the px, py, and pz orbitals. It is found in compounds where carbon is singly bonded to other elements. Examples: alkanes and amides. The shape is tetrahedral. The bond angle is 109.5 degrees. The percentage characteristics of this orbital include, like, now the s orbital is 25 degrees and the 3p orbital sum up to 75. Now, like the same thing I did before, 100 in 4 places, 100 all over 4, that's going to give us 25. So 25, the s can take 125, then 25 times 3 actually give us 75, and that percentage is going to be for the p. Okay, now I'm going to show you how to represent this. Now look at number 1, the s orbital. This is the s. I'm trying to minimize the space of the board. This is the px orbital. px. This is the py orbital, py, and this is the pz orbital. It's meant to be bulging out, like I said before, but since we can't do that in a 2D dimension, so we have to leave it as this. This is the pz orbital. Now, when all of this mix, they form a tetrahedral shape like this. We're always saying it like the s orbital is always in the middle, and this is what they form. This is the shape. If they ask you to represent it diagrammatically, we have to represent it in that way. Now, example is, like I said, alkanes, 4 bonded, like they have 4 bonds that actually like combine with. Now, if you want to talk about the strength and everything of this orbital, the strength increases, like, what should I say, SP is stronger than SP2, and that is stronger than SP3. This is for the strength. Oh, let me put the arrow backward. Let me just leave it. This is it. This is for the strength. This is the strength trend. Now, for the this is strength trend. Now for the bond length strength. The bond length strength increases in the opposite order from SP3. It goes to SP2. It goes to SP. That means SP3 is longer than SP2 and is longer than SP. So this is the bond length strength. Bond length. Okay, this is where we'll be stopping in this video. Thank you for your time. Please like and subscribe to this channel. Thank you.